तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yeah, so let us start today with discussing the connection between symmetry, invariance and conservation principles, which is what I mentioned the last time. Symmetry leading to invariance, leading in turn to a conservation law. And this is captured in this theorem called Noether's theorem. The full power of this theorem is actually apparent only when you do field theory, continuous number of degrees of freedom, both classical as well as quantum, but we will talk about it in the context of plane mechanics, Lagrangian mechanics. And the idea is the following. We have kind of skirted around this whole thing back and forth without ever formalizing it. I mentioned that in Hamiltonian dynamics you have a set of constants of the motion in involution with the Hamiltonian, and if you have a sufficient number of them then you end up with an integrable system. Now the point is that every time you have a constant of the motion, not only do you reduce the difficulty of solving the dynamical equations, but you actually get a little more information. You get some information about the symmetry of the system, and this is the idea behind constants of the motion. And the idea, the point that they are the significance of the fact that they are in involution with each other helps you via the Liouville-Arnold theorem to show integrability and so on, and we saw a little bit of what the geometrical implications were. We should now like to look at what the algebraic implications are. The idea is that if you have a constant of the motion in Hamiltonian dynamics, that quantity serves as the generator, as a generator of a group of transformations called the symmetry transformations of the system, under which the system's equations of motion do not change at all. So generators of symmetry transformations come from constants of the motion. So that is really what the algebraic significance of a constant of the motion is, and we will see examples of this. Noether's theorem helps you to find these constants. So let me start by, in very naive terms, by asking what is meant by a symmetry. By a symmetry I mean, by example for instance, some set of transformations under which the problem does not change in a very general sense. If I look at the problem of a particle in a central potential, then both the kinetic energy as well as the potential energy are invariant, unchanged under a rotation of the coordinate axis. So I would say this problem has spherical symmetry, because transformations which take you from one orientation of coordinate axis to another orientation do not seem to affect the Lagrangian or the Hamiltonian. Therefore you would expect that the set of solutions of the problem would remain unchanged. Not an individual solution, that would of course change, but an individual solution would go to some other solution, look like some other solution under the transformation of coordinates, and the set of solutions would be unchanged, or the equations of motion would remain unchanged in form. This is what I would mean by a symmetry, a dynamical symmetry of a system, something where the equations of motion do not change. The moment you have this symmetry, it means there is an invariance under a certain group of transformations or set of transformations. Noether's theorem then tells you how to find the corresponding constant of the motion, okay, and this is how it goes. I start by doing this in Lagrangian mechanics. We could translate this to Hamiltonian mechanics subsequently. So I start with an L which is a function of some q dot, and if it is a non-autonomous system there is also a t sitting there, and of course we write the Euler-Lagrange equations down, and the Euler-Lagrange equations are delta L over delta q is d over dt delta q I dot, and this is true for each degree of freedom I running from 1 to up to n if you have an n freedom system. Okay. And this stands here, this is a shorthand for all the qi's, and this is for all the qi dots. Okay. Now on the solution, on a solution trajectory, this equation is satisfied, of course, and of course the solution becomes unique once you specify a sufficient number of initial conditions. Okay. Now the point is, if I make some transformation such as changing the coordinate system or shifting the origin of the coordinate system or anything else at all, I make some transformation of some kind on the variables, then I ask what is the change in the Lagrangian as a consequence of this transformation. That change let me denote by capital delta L. I do not want to use little delta L because I use that for variations which led me to derive the Euler-Lagrange equations. Let us call it delta L, and I will give examples. This delta L of course is equal to delta L over delta Q, there is a summation over I implied here, so we will not write this explicitly. If delta Q is the change induced in the coordinate Q under this transformation, plus delta L over delta Q dot, if this change does not affect time, of course there are transformations where you may even change the time, you may scale the time or shift the time origin and so on. For the moment let us not look at those cases. Then this is the change in the Lagrangian. Okay. L goes to L prime, which is given by this quantity here, but now we are interested in what happens on a solution trajectory always. Therefore on such a trajectory delta L by delta Q satisfies this equation here, and you put that in and you immediately see this, by the way, is d over dt of delta Q, because this change has nothing to do with time evolution or anything like that. I have one set of coordinates, I make some change of variables, and I have another set of coordinates, and therefore the d over dt operation here commutes with this delta operation. Okay. And therefore I can write the delta Q dot as d over dt of delta Q, and I put in this expression here, and you can see immediately that this becomes a total derivative. Okay. So I have assumed that I make an infinitesimal change of variables, transformation on the coordinates for instance, and that is delta Q, and immediately there is a change in the Lagrangian which is d over dt of this guy here. You recognize that this is just for if this were qi dot, this is just pi by definition, the conjugate momentum here. So we could write this as d over dt. So let us put in all the i's. D over dt of pi delta q. So using the Euler-Lagrange equations I can write an arbitrary infinitesimal change in the coordinates in this form, in the form of a total derivative. On the other hand, I know that the action does not change and the equations of motion do not change if the change in the Lagrangian is a total derivative of some function of the coordinates and time. So I also know that there is invariance provided the equations of motion do not change, provided delta L is also equal to d over dt some function of the coordinates and time, and I am imagining infinitesimal transformation. So let me pull out that infinitesimal always and write this as some epsilon times f of q and t. So this is just a scale factor to tell me this is a first order infinitesimal, the same order as delta q and delta q dot. Okay. So if, this is a big if under that transformation it turns out that delta L is of this form without using the Lagrangian, without using the Euler Lagrange equations, because that has been used there, without using this, then on the one hand using the equations of motion tells you that delta L must be of this form. Directly calculating depending on what the transformation was tells you that delta L is of this form, if it is of this form. This immediately implies of course that these two must be equal, implies that Pi delta Qi minus epsilon f is a constant of the motion, because d over dt of that is 0 on the solution set. This is the content of Noether's theorem. Of course I have said this in the simplest way possible, the whole thing is made much more general, it applies to fields, it applies to relativistic cases and so on and so forth, quantum field theory, etc. But in ordinary Lagrangian mechanics this is the way the theorem goes. So please notice the ingredients that have gone in. On the one hand, if I take some arbitrary coordinate transformation or any transformation whatsoever, and it should turn out first order infinitesimal transformation, and it should turn out that the Lagrangian change in the Lagrangian is a total derivative, you set that aside, but then using the equations of motion and the fact that L is a function of q, q dot and t, the change in the Lagrangian is expressible in this form, then equating these two fellows you conclude that this combination must be a constant in time as the system evolves. So this is how you derive the actual expression for a constant of the motion. Now let us try and apply this right away, and let us apply this to a simple case of a particle moving in some potential. Yeah.
How did we get that total derivative?
Pardon me? How did I get which derivative?
d by dt of epsilon
If it turns out that I have to tell you what the transformation is, I put it into the Lagrangian and ask what is the change in the Lagrangian directly without using the equations of motion, and if it turns out to be this, then these two are guaranteed to be equal.
So then how is the difference a constant of motion?
Because d over dt of it must be 0, d over dt of this is equal to that, so d over dt of that minus this is equal to 0, total derivative, and therefore it is a constant of the motion, right. Okay. Now let us apply this. I know that if I take a particle in some potential, say a central potential for example, so let us see what happens then. So I start with L for a single particle equal to the kinetic energy half m xi dot squared, x1 dot squared plus x2 dot squared plus x3 dot squared if you like, or if you like half m v vector squared minus some potential v, and let us say it is a central potential for example, it does not have to be, it is a central potential for instance. It is clear that if I change the origin of coordinates nothing should have happened, nothing should happen at all. So how do I show that the momentum is conserved as a consequence of this? Let us take an even simpler example, free particle, no potential at all. In this case the linear momentum is conserved, the reason is that the system is invariant under a translation of the origin. So let us go from r to r prime equal to r plus a vector epsilon, an infinitesimal amount, I shift the origin by an infinitesimal amount. It is immediately clear that v goes to v itself because d over dt of this is 0. Therefore this Lagrangian is invariant under a translation of the origin. So let us plug that in. into this business, and what do you get here? It tells you that delta L is identically equal to 0 in this case, because there is no change at all. R dot is the same as R prime dot, so delta L happens to be 0, which implies that this portion goes away and you are left with this, and that is supposed to be constant. So what does that give you? For each component, what does it tell you? It says Pi times delta Q, that is epsilon, each epsilon. Independently I take 3 different directions and I translate, and each component P1 epsilon 1 is constant, P2 epsilon 2 is constant, P3 epsilon 3 is constant. So it tells you this implies that P equal to constant. So this says that if your Lagrangian is invariant under a translation of the origin of coordinates, then the linear momentum is a constant. This is a rather trivial example, so we need to do a little better than this. So now let us put a potential and see what happens. The moment I put a potential, linear momentum is not constant anymore because there is a force on the system. The rate of change of force, rate of change of momentum is equal to the force, so the momentum is not a constant anymore. So let us put a central potential and see what happens. Minus V of r. Now this is no longer true, but I know that under rotations of the coordinate system the Lagrangian does not change once again. That is obvious just by looking at it, because the rotation of the coordinate system keeps distances unchanged, and therefore V of r is unchanged, and definitely p squared is a scalar, so that does not change at all. Now what does a rotation do? We have to now look at a rotation matrix and ask what an infinitesimal rotation does. So let us do that. So we have r goes to r prime under a rotation r of n psi, a rotation of the coordinate system through an axis, about an axis n, through an angle psi. We have a general formula for this. We should really need just an infinitesimal version of this, which is much simpler, but I have not derived that explicitly. You could write rotation matrices and do it, or we could take a special case. We could say the rotation occurs in the xy plane, then I can write a very simple formula, or the yz or zx, but I want to do general. I want to show you that take an arbitrary direction and I rotate and nothing changes, and let that direction be the unit vector n. Now I know that we already have a formula for the rotation of a finite by a finite amount of this vector, and if you recall, this quantity was equal to cos theta times r plus 1 minus cos theta, cos psi, 1 minus cos psi, and then it was n dot r n plus sin psi n cross r. This is what finite rotation did to a vector r. So I take an arbitrary vector r, I rotate the coordinate system about a unit vector n through an angle psi, and this is the new vector. I am interested in an infinitesimal transformation, infinitesimal rotation. So instead of psi I go replace it by an epsilon and work to first order an epsilon. Then what does r do? Well, cos psi to first order in epsilon is just 1 itself, so this is r. This goes away, this cancels out, but this remains, and sin psi is psi itself. So plus epsilon n cross r. It is easy to verify that this is indeed what happens if you change the coordinates. If you rotate by an infinitesimal amount, this is what any vector r does. There is a portion which is proportional to n cross r. So in this case we know what the change in coordinates is. We know that delta r is equal to epsilon n cross r. Therefore what happens to L? And what happens to L? Does this change? Does this change at all? It is a scalar, so this does not change at all. Does that change? It does not, because it depends, r prime is equal to mod r prime equal to mod r, so that does not change. So delta L in this case is also 0, quite trivially 0. So what is the constant of motion here? You have only this, and this is p dot delta r, and you remove the epsilon, it is true for every epsilon. So what is the constant of motion? It says p dot n cross r, which is also equal to n dot r cross p. You do cyclic permutation to this, or L dot n. The component of the angular momentum about the direction of rotation is constant. But this is true for every n. I could have chosen any arbitrary n, therefore angular momentum is constant. So this tells you that angular momentum conservation is a consequence of rotational invariance, just as linear momentum conservation was a consequence of translational invariance. If the invariance is lost, you do not have this anymore. These were cases where delta L was 0, this portion ended up being 0. Let us look at a very simple case, an even simpler case than all this, where delta L is not 0, and you get a constant of the motion which may even be time dependent. So let us look at that. In fact, it can help you even solve the equations of motion, in this case completely trivial. So let us look at the problem of a particle moving in the vertical direction under gravity. So L is equal to half m z dot squared minus mg z. The problem dropping from the vertical height, from a given height it falls down. This is the Lagrangian of the particle. I am only interested in the z direction in the motion here. Now I ask, what happens under z goes to z plus epsilon? I know that if I change the reference level, the physics does not change. I add a constant to the potential energy, it does not change. So I would like to see if this invariance of the equations of motion leads to a constant of the motion or not. The Lagrangian itself changes, of course, when z goes to z plus epsilon this changes, but then you say, that is just an addition of a constant to the potential energy, so if I differentiate and find the Euler-Lagrange equations they will not change. So it is apparent that they do not here. Well, let us work this formally and see what happens. In this case delta L equal to minus mg epsilon. This is the change in the Lagrangian, but we also know that delta L over delta z dot, this guy which is the momentum p times delta q, so p times delta z equal to p times epsilon. So we have on the one hand the change in the Lagrangian must be equal to d over dt of p epsilon by using the equations of motion or the Euler-Lagrange equation, but this must also be equal to this quantity here, which should be writable as a total time derivative, and that of course is completely trivial because I can write this as d over dt of minus mg epsilon t. Okay. Put a t there. So you are guaranteed that P equal to minus mg t plus constant. Right. That is of course true. It says the velocity depends on what your initial condition is, that constant of the motion is the initial condition, and it helps you to solve this problem, because if I now put P equal to mz dot, it says it is initial velocity minus half gt squared, initial position minus half gt squared, and so on and so forth. So it solves the equation of motion in this particular case. But notice this trick here, this was necessary for me to be able to use this as a guaranteed constant of the motion and therefore find the first integral and solve the problem. So here is a case where you need that delta L part completely, it was vital, in fact that is where all the physics was, everything was sitting inside here. One can now do this in more general cases, etc. You remember long ago we looked at a charged particle in an electromagnetic field, and then I said that under a gauge transformation of the potentials, the Lagrangian changed by a total derivative of a function of coordinates and time, right. So that was a case where you explicitly had a delta L with the function f sitting, it was in fact the gauge function. And now you should ask, what quantity is conserved as a consequence of this? Well, in the mechanics case it becomes completely trivial, unfortunately, because now the initial portion of it, the change in the coordinates, what kind of change do you have in the coordinates? I make a change in the gauge, I do not do anything to the coordinates at all. So in that case the first part of this constant of the motion, the first portion vanishes, and it is only the second part that is involved, and you get charge conservation. But we know that charge is already conserved, so in a particle picture. In a field this is different, this will actually give you a conserved current, it tells you the continuity equation, gives you the current, the appropriate current. So if we want to find in a field which is interacting with the electromagnetic field, for instance, what is the conserved current, you have to go through this procedure, and Noether's theorem will give you the conserved current. And recall that from conserved quantities, things which satisfy equations like continuity equations, you derive conservation laws. Let me do that, recall this to you very briefly. If I have an equation like this equal to 0, then the standard way of finding a conserved law, conservation principle, is to integrate over an enormous large sphere and then assume that J vanishes out there. So what we are talking about is currents and charges moving about in some finite region of space, and I integrate over a very large sphere where there are no currents at all. Then this thing says, if I integrate over dV of this whole thing, I still get a 0, and of course if the volume is one large fixed volume, which I am going to let go to infinity eventually, this first term gives you d over dt of integral rho dV. It is now a total derivative because the range of integration is independent of time, and therefore I can bring it out and it becomes a total time derivative, and this plus integral j dot ds equal to 0. This of course is the total charge in the system, so, or the total mass or whatever, plus, provided this current vanishes on that surface, provided all your devices and charges and currents are moving in some finite region of space and the current is actually 0 out there, this equal to 0 implies Q is conserved. This term may not be 0 sometimes, there could be something at infinity or flux at infinity, in which case you have to include that also. So this is the standard way in which you go from a local equation of continuity to a global conservation law in this fashion. and this is more fundamental because this is really saying something at local points as opposed to this is a global integral, and all our equations in physics are all local statements. They always tell you that if you move something here a little bit, something near it is affected and so on, rather than global statements. Any integral statements are actually derived from local statements, like Maxwell's equations in the local form as opposed to Faraday's law of induction in the global form. You have to start with the local statement and then you derive the global statement, the integral form. Okay. We talked about translation of the coordinate axes. So r goes to r plus some epsilon. We talked about a rotation, r goes to r prime, which is a rotation matrix acting on r. We could also ask what happens when the t goes to t plus epsilon. I could induce a change by changing the origin of time and asking, do the equations of motion remain unchanged? If the laws do not change with time, then I have time translation invariance. I am going to leave it to you as to work out and find out what the conserved quantity is in that case. What would it be? It would be the generator of time translations. What is the generator of time translations? Yeah, the Hamiltonian. The Hamiltonian generates time translations. Time evolution is given by the Hamiltonian itself, right? So in this case it is obvious that this is so. In the Hamiltonian picture, remember that evolution under time under a Hamiltonian was itself a canonical transformation, because we know that if q at time 0, qi 0 pj 0 was equal to delta ij, then we know we are guaranteed under Hamiltonian evolution that this is also true. So evolution under a Hamiltonian is itself a canonical transformation. The coordinate at some, so if you start here and you go there and this is q at 0, p at 0, and this is q at any time t, p at time t in some phase space, then you can look upon this in two different ways. One is you fix your coordinates, this is your initial state condition, and as time evolves this point in phase space, this state moves to that state. That is one way of looking at it. Another way to say is that this is just a transformed version of this in another coordinate system, and that transformation is a canonical transformation. In that sense, time evolution is just the gradual unfolding of a sequence of infinitesimal canonical transformations. Each q and p, a little delta t later gives you another q and p, which is a canonical transformation of the original, an infinitesimal one, and therefore a symplectic transformation, and so on and so forth as it goes along. The analog of this in quantum mechanics is that evolution under a time independent, evolution under a Hermitian Hamiltonian is a unitary evolution. Probabilities are conserved. What is conserved here in Hamiltonian flow? In general, what is conserved? The volumes are conserved. The density obeys Liouville's theorem, and therefore volumes are preserved here. Corresponding thing in quantum mechanics is that probability is conserved, as we will see. Okay. We talked a little bit about generators and the algebra of generators, not too much I am afraid. But what I would like to do now is to move on to relativity, introduce special relativity, talk about the Lorentz group, and then try to link some of those ideas with the ideas we had earlier about generators. We did a little bit about symplectic transformations. Now we are going to generalize this and do a little bit more about Lorentz transformations. And of course one can do this in many ways. I am assuming that you already have some familiarity with special relativity, but I will state the facts here and then write down the equations, and we will try to look at this from the point of view of symmetry transformations. This is the way we would like to approach this subject. The idea is that in Newtonian mechanics it has been found that the laws themselves do not change if you make a translation of the coordinate axes, if you make a rotation of the coordinate axis, these are purely spatial transformations. Time itself is supposed to flow inexorably from the past to the future and is not a dynamical variable in Newtonian mechanics, and these are the two invariances. But you also have invariance under of all physical laws when you move from one inertial frame to another inertial frame, and this was Newton and Galileo's big insight, namely the laws do not change in form if they are written down in two different frames of reference which are related to each other by the fact that one of them is that each of them is moving at a uniform speed with velocity with respect to the other. So anything which is just a pure velocity transformation does not change the form of the equations of motion. This is no longer true if you have accelerations. If you have an accelerating frame of reference, the form of the laws in that accelerating frame may be very different from the form of the laws in an inertial frame. Of course Newton's big input, which turned out to be not quite right, was that he chose a preferred set of coordinate axes frames. He chose a set of inertial frames. He said these are inertial, all frames which are fixed with respect to the fixed stars, as he put it, are inertial. So what has happened there is that what happened was that a set of frames got chosen as a preferred set of frame, and there is no such preferred set. This is what we know now. So in a sense he was almost there. The principle of relativity was already there, the postulate of relativity was missing, and this is what we are going to write down. Okay. So let me write this down and say the principle physical laws. Necessarily it is a little vague here, but we will make it precise. Form invariant, that is they do not change in form in appearance, a form invariant translations of the coordinate axes, rotations of the coordinate axes, translation in time, in other words a shift of the origin of time. This is what I mean by translation in time. And from one inertial frame to another. By that I mean two frames of reference connected by a velocity transformation. The other frame moves at uniform velocity with respect to the given original frame. Of course, as I said, he defined a set of inertial frames as those frames which are fixed with respect to the fixed stars or something. Now you could ask, what do you do on a cloudy day when you can't see the fixed stars? How do you know you are in an inertial frame? Well, the correct way of defining this is to say an inertial frame is one where Newton's first law of motion is valid. If you discover, if you roll a ball on a floor and it turns out and it has no friction and so on and it keeps going forever at uniform speed, then you know you are in an inertial frame. Now this becomes a matter of measuring and precision and so on, so we are not going to get into that. On the other hand, there is an unambiguous way of defining what an inertial frame is in Einstein's relativity, and that is we are working in flat space time, no curvature of space, no gravitational fields at all. Then you can define an inertial frame and other frames inertial with respect to it, and there is no such thing as a frame fixed with respect to the fixed stars or anything like that. This is not needed. So you simply examine if your region of space time is flat in a specific sense, then all frames moving with respect to you at uniform velocity are inertial frames. Now we already know in Newtonian mechanics that the moment you go to a non-inertial frame, Newton's law is not valid. Newton's law of motion is not valid because we know that there exist pseudo forces. So if you insist on writing mass times acceleration is equal to the force, on the right hand side you have to put compensating terms to take into account the fact that your frame is in acceleration. Those are called pseudo forces. They really should be called pseudo inertial or non-inertial forces or pseudo accelerations, and you multiply it by mass and then you get a pseudo force. So I am assuming that you are already familiar with the idea that you have a centrifugal force or a Coriolis force or an Euler force and so on. So I will not go into that, but now let us focus on this principle here and ask what does this imply. Okay. Translations of the coordinate axes have 3 generators, the 3 directions. So there are 3 generators here. Let us count parameters. We have 3 here, you have 3 here, 3 Euler angles or the n and the psi we talked about. So you have 3 more here. Translation in time, 1 here, 1 inertial frame to another, how many components do you have? Well, you could go in any direction. This velocity could be in any direction with respect to your fixed coordinate system, and therefore you have 3 velocity parameters, and you have 3 plus 3 6 plus 1 7 plus 3. So this is a 10 parameter group. And these transformations can be shown to form a group satisfying the axioms required of a group, namely there is a group composition law, there is an inverse, there is an identity, and the group composition law is associative, namely I compose 2 elements and then compose it with a third, it is the same as doing it in either order. So G1, G2, G3. That was the group associative law, and that is also needed for a group as was pointed out. And this group here is called the Euclidean group, is called the Galilean group. Okay. It is a 10 parameter group, it is a fairly intricate group, and it has got complicated portions. You can see that the translations form an abelian subgroup, because these fellows can be done in either order, but the rotations do not, and then the question is, do these fellows form a group or not, etc. So there are deep technical questions involved here. Now what Einstein's postulate did, what Einstein's insight did, was to add to this the all important postulate of relativity. And since he did this in the context of light, of Maxwell's equations, he was specifically interested in the invariance of Maxwell's equations, the postulate was made in terms with reference to the speed of light in vacuum, but actually the statement is independent of that. The statement is there exists a fundamental velocity which is the same in all frames of reference, and so happens that light in vacuum provides a physical manifestation of this fundamental velocity. It is an entity which travels at this fundamental velocity, but let us write it in the conventional way. Is constant independent of the state of motion of the source or the observer or the receiver. Is denoted by C. With that single input, this is a physical input now. Please notice that the rest of it had to do with general forms of laws and was not specific to any particular phenomenon. On the other hand, this is specific, it is a physical input, it says something about a physical parameter. It was lucky that we have an entity which travels at this fundamental velocity, otherwise it should have been much more difficult to discover this invariance here. Now what it implies immediately are the Lorentz transformation equations, and I would like to focus on that. This implies the following, and here is the derivation of these equations. Just as you derive what rotations do by requiring that a certain form is kept unchanged, namely the distance of a point from the origin is unchanged under a rotation of the coordinate axis, this told you immediately that rotations are orthogonal matrices, are represented by orthogonal matrices. In exactly the same way, this is going to tell us what sort of transformations can you possibly have. The idea is that if you have two frames of reference in which the origins coincide at t equal to 0, and say one frame is moving at uniform speed with respect to the other along the x axis for instance, and at t equal to 0 in both frames a pulse of light is emitted, this pulse travels as a spherical wave. Then the first person in the frame S, and you have S prime moving along like this in this direction, in the frame S c squared t squared equal to r squared, and that is the shape of this pulse. It is a spherical pulse. At time t it has reached a distance ct from the origin. In the other frame he sees exactly the same thing, c squared t prime squared equal to r prime squared, and c is the same in both frames, and you impose this. This is the content of this statement here. The moment you do that, you have this possibility. You have c squared t squared minus r squared must be equal to c squared t prime squared minus r prime squared. Then in Newtonian mechanics c is essentially infinite. There is only a way of sustaining this equation without changing t. If you say t equal to t prime, which is what Newtonian mechanics does, then the only way of sustaining this equation is to make c infinite. But in relativistic mechanics, and this was Einstein's insight, this is some kind of hyperbola. That is some kind of hyperbola here, right. It is the invariance of this form that is required, and this form can be kept invariant in more than one way, and the second way is that t changes and r changes, t becomes t prime, r becomes r prime, such that this quantity is kept unchanged. Remember, for ordinary rotations you insisted that r prime squared equal to r squared. Now you are saying this quantity is equal to that quantity, and then you ask what are the possible transformations under which this can happen, and this is how the Lorentz transformation is derived, and it is very well known to you that the consequence is immediately the following. In this situation I have pictured where this guy is moving at speed v along the x axis, we know that this implies that x prime is equal to x minus vt over square root of 1 minus v squared by c squared, y prime is y, z prime is z, and t prime, let us write t prime in the beginning. So those are the solutions to the equations which tell you that this hyperbolic form should be kept unchanged. And of course now we want a better notation. I would like to combine x as well as t, x, y, z and t. So I would like to make this have the same dimensions as length, and let us multiply it by c. So you have ct minus xv over c over the square root. Okay. Is this correct? Yeah. and the standard way of writing this is now to introduce a 4-dimensional vector. So I will introduce x mu equal to Ct x y z, okay, and I will call this x naught, I call this x1, x2, x3. I put a superscript rather than a subscript, it will become clear why. This quantity which satisfies these equations, these transformation equations, is called a 4 vector, and the group of transformations under which this form is invariant is the Lorentz group. Just as you had the rotation group earlier, this is the Lorentz group, and it will turn out very shortly that it is representable by 4x4 matrices which act on these coordinates, because these are like column vectors. I am going to write one below the other, and these 4x4 matrices would not keep, but are not orthogonal, these matrices are not orthogonal, but rather they keep this form invariant, and therefore they are pseudo orthogonal, and it is written as SO31, and this is called the Lorentz group, special Lorentz group. 3 and 1, because I am going to introduce a metric and there are 3 space like directions and 1 time like direction, taking into account the fact that in this quadratic form there is a minus sign here. So there is a c squared t squared minus x squared minus y squared minus z squared, and I want to take that into account. Okay. So this quantity I call a 4 vector. Sometimes called upstairs is called a contravariant vector. In old tensor analysis, anything with a superscript of this kind is called a contravariant vector. Then I define a metric tensor, G mu nu, which is given by such that G00 equal to 1, G11 equal to G22, I am doing this very badly, I should do this a little more systematically. The square if you have a space-time point x mu and a space-time point x mu plus dx mu, then the square ds whole squared equal to c squared dt squared minus dr squared is called the square of the interval between these 2 points. Under a Lorentz transformation, this interval is unchanged, it is a scalar, and that was the whole point. This quantity here can be written in compact notation. Oh, I should now define contraction and so on. Let me do this next time slowly and carefully. I should define for you the lowering index, how to lower it, what is meant by a covariant vector and so on. I wanted to do this properly. I do not want to just define it as something which is done with the G mu nu. I want to show you that you really have a vector and you have what is called a covector in a dual space. Since I want to do that properly, let me do this next time. Let me do this, I may run out of time. I should do this properly. Let me ask you, how much of relativity are you already familiar with? Yes? You
encountered the transformation.
You encountered the transformation in this form.
Then the what?
Pardon me? In this form. Okay. Okay. And then what?
Then arbitrary derivation of Lorentz contraction.
Lorentz contraction and time dilation, length contraction and time dilation. Yeah, those are trivial consequences. But the fact that these things form a group, is that been emphasized? This is the question. This is the point. This is what we must look at. Let me do that. I will do that properly so that you see. You have to understand that Lorentz transformations involve not only velocity transformations like this, but also rotations of the coordinate axis. So, and you do not have to go along the x axis, you could go in any arbitrary direction and rotate, and then you can shift the origin. So all these are possible and they form a 10 parameter group once again. So the set of rotations, the set of translations in space, the set of the translations in time, as well as velocity transformations, they again form a 10 parameter group, but the transformations leave a form like this invariant, and this makes all the difference. Now this group is not the Galilean group, it is called the inhomogeneous Lorentz group or the Poincare group, of which the special Lorentz group, this is a subset, this is a subgroup here. And this is the group of homogeneous transformations which do not change, which do not shift the origin of space or time. So we need to understand that, and we also need to understand that the structure of this whole thing, the structure of this group is such that it is not orthogonal, not represented by orthogonal matrices, but by the kind of strange pseudo orthogonal matrices. We need to recognize that, and above all it will become clear that the rotations actually form a subgroup, but the velocity transformations do not, and this is important. If I move to another frame moving along from S to S prime, and then from here I move to an S double prime which is moving with the speed V double prime in the same origin, then this is S double prime is related to S by a Lorentz transformation. But if this fellow was moving in this other direction, this is S double prime with a V prime in the vertical direction, then these transformations do not form a group among themselves. These are called boosts, because you give a boost to a frame of reference and get it moving. So the boosts do not form a subgroup, and that is what complicates matters. The rotations form a subgroup and the boosts do not form a subgroup, but the boosts and rotations together form a big group here. So the complicated things can happen. So you move like this and then you move like that, it could be as if there is a rotation also effectively. So my aim is to make you understand that this is what I would like to focus on, and I would like to use an efficient notation. This 4 vector notation is extremely efficient because it will tell you what is a scalar, what is a vector, what is a tensor, and so on, just like we use scalars and vectors in ordinary mechanics, and it is much more convenient. I would like to use this notation. So that is I have to lay the groundwork a little better. I will do that. Okay.